color-kinematics. Sorry?
That was from Zoom recording.
Okay. Duality. Sometimes it's known in the literature as BCG relations. I will explain to you. And this is pretty hard subject to understand formally. So this is ongoing. I think it will be at least 2 papers, maybe 3, with Mar and Shahar and Francesca Vanek. Okay, what I'm going to talk about, I'm going to talk about perturbation theory. Perturbation theory in quantum field theories, and in particular in gauge theories. So typically, what's a perturbation theory, right? This is something very simple. You take the integral, and for example, you write something as eta ij I xj plus 1 over 3 factorial wij k xi xj xk. And then you expand these guys up there, right? So typically, something dx, dx, for example, dx, x, etc. And then you basically look at your integral perturbation. And what's important thing that, for example, you can encode all your perturbation theory in diagrammatics and combinatorics, so you can construct the things, for example, according to the theorem, either this, you can do it either this, etc. So it's a very algorithmic way of doing things. Then, of course, so this is very good small level for perturbation theory, just finite dimensional integrals. But of course, what I will be interested in is also do perturbation theory when what people call these external states. So if I will try to calculate the integral like this, so if I put xa1, xi n, then I will write this integral. So if here will, I mean, all my pictures, all my graphs will be what's called vacuum graphs, so there would be no external edges. While here, I will start to do this. 1 over 3 factorial. So if I start to depict this diagrammatically, then these guys will have external legs. So for example, I will have something like, so if let's say I will have 4 guys here, then I will start to have diagrams, for example, like this, etc. Right. So in field theory, when you go to field theory, model a lot of details. These guys becomes infinite dimensional, so you deal with operators, and correspondingly, your inverse is what you attach to the line becomes just green function, etc. And so modular, whatever, what's called infrared UV problems. I mean, formally, everything goes through. Then there is very interesting gadget, which is gauge theory. So for us, it will be basically, we will deal with the Lie algebra, with quadratic Lie algebra. I will have 2 types of data. So of course I will have invariant metric. So for example, I will have TA, TD is equal to 1 over 2 at AB. And then of course I will have a structure constant. So I use notations which I will use later on. Okay. So then generally in perturbation theory, what happened that this operator perturbation theory is not well defined. This operator is not invertible, and you have to do some black magic to make things invertible. Okay. Then what's important thing that, again, there is a very, very complicated gadget which goes to perturbation theory in gauge theory, but what did people realize at some point is the following thing. And again, I would assume that you don't know much about physics, amplitudes, etc. So I will basically try to say it you abstract. So when you do perturbation theory for the gauge theory, so you have this Lie algebra data, you have some data attached to the theory. So all your amplitudes typically, endpoint amplitude, so endpoint amplitude, point amplitude is organized in the following. So amplitude will have some external guys coming in, and roughly speaking, it will look like follows. So it will be a sum of graphs, with some set of graphs, and then there will be two type of factors, Ci and I, then there will be Di. So Ci is, I will give you example in a moment. So Ci is called color factor. Color factor. So it's constructs entirely from Lie algebra data attached to the graph. Then Ni will be a kinematic factor. And then Di typically is what's called scalar propagator. And what's important thing that this object should be well be invariant. So one of the issues is, so this is what people in physics call gauge invariant object. Gauge invariant object. So let me give you an example that it doesn't look very abstract. So let's go to and we have 4 entries. Okay, and so we'll have 4 type of graphs there. So we'll have this graph. So that maybe is A, B, C, D. Then I will have this graph. This is the only way I can construct. And then there will be this graph. A, B, C, D. So in principle, you can figure out this graph. So if you put here 4 axes, but you have just here cubic interaction and up to overall combinatorics, this is the only construction you can do. Okay. So let's discuss how this answer. So what's important thing that this is what people realized in the community by doing many calculations, that the theories can be messy, but after a while they're always organized in sort of this very simple form. So what's a color factor here? So this diagram quite often called S diagram or S channel. This is T channel. This is U channel. So the color factors will be the following. So if I write this attached to this graph, this will be just 2 construction of structure constants of A, B, L, F, L, C, D. So I'm using, again, I'm putting on every vertex structure constant with all indices down, and I'm using this internal edge to contract with the metric. So this is the starting thing. And when I'm writing this CT guy, then I will have F, B, T, L, F, L, C, A. And then finally I have this guy, F, D, L, C, B. Okay. So now if you write the answer, right, so this diagram will be written as correspondently C S and S ds plus C T and T T plus CU and U du. And also what you can realize very easily that if you look at the sum of this, same color factors, they are zero because Jacobi identity. So this guy plus this guy plus this guy is equal to zero. Okay. So now typically when you calculate diagrams, what's important that, these factors, they do not have any intrinsic meaning. Only this object is have intrinsic meaning. Because the way you write the answer, what's important that your Ni can be shifted always by Ni plus di alpha, whatever, right? Because if I shift my amplitude like this, A4, so if I shift it, then under this shift, what you can see that what I get A4 plus alpha CS plus CT plus E.
Which is like just a number here, or what kind of quantity is alpha?
So alpha is whatever. So in practice, you have theories and you have many momenta, etc. So it can be very complicated combinations of momentum, some in data, external, etc. This is just sort of numbers. This is this objects, and this is again typically some p squares. Okay. But what's important, if you take individual diagram, this combination has no invariant, meaning you put everything together, and this is what people call gauge invariant thing. And again, let me say very clearly, you take a concrete theory, I don't know, you take a Young-Mills, to calculate these numbers, you have to don't do PhD, whatever. It's technically complicated. But the answer eventually, of course, organized in this form.
Do you see alpha just a number, or is it?
No, it can be any combination of momentum, for example, anything. It can be a function. In a way, it's independent because I shift by this di alpha, this vanished by Jacobi, so this is what's called gauge invariance. Okay, so this is all pretty standard. But then what people realized like 15 years ago, this is exactly what goes. So you see, these objects are not uniquely defined. But then people experimentally realized, and this is exactly goes under the name of color-kinematics duality, or BCG relations, is the following thing, that there exists a choice, and you can choose this ends which satisfy the same type of identity. Let's think, it has been conjectured again. Let me say, this is experimental fact. It's not proven, but it's experimental fact. You take a theory, you calculate it, you get it. You take a theory, you do the things, you put on a computer, whatever, you calculate, you go to loops. So you always can make a choice. And of course, what people do in practice, all this amplitude community, it's not that, they do Feynman diagrams, they have some other methods, but there is always exists a choice when these kinematic factors will satisfy some algebra. And this is what people call, whatever it means, kinematic algebra. And of course, it's true, for Young-Mills. Again, it's at the level of experiments or combinatorial proofs, people were able to prove it. So I think in Young-Mills at level of trees, it's not understood conceptually, but technically you can prove that exists this choice. So it means that there exists some gauge choice when your momentum combination will satisfy Jacobi-like identities.
So what are these ends? Can you explain what the C's are?
And so ends, imagine, so you have a complicated theory and typically will characterize some data coming particles by momentum, right? So these ends are particular combinations of momentum, some functions of momentum, which may differ from theory to theory. But what's amazing is that there exists a particular choice. And again, this combination of momenta, they do not have any universal meaning. You work in one gauge, you get one particular combination of momenta associated to diagram. You work in another gauge, you get another thing. But then eventually what people observe that, you can have a choice when this is always works.
And it's just wondering because you gave this very concrete examples and I explained what the C's were in this example, but then you didn't say what the N's were in the example.
Let me do a Chen-Simons example, because if I go to Young Bill, I don't want to give a, let me give you example about Chen-Simons, okay?
I have a terminology question. Yeah, is there a reason that's not called a choice of gauge and it's called a kinematic algebra?
No, but it's a choice of gauge, but what's important thing that this choice of gauge has very beautiful algebraic structures, right? I mean, basically this object start to look like there is some underlying Lie algebra behind it, okay? So, and then there is, let me not spend too much time, but then there is another statement which I'm not going to discuss, but another experimental fact that if you start to do things, so if you take this choice, particular choice, you can quite often associate another theory when in this things you replace, you just try to sum of these guys. So you just remove color factor and you put an I with this choice. And this typically, again, experimentally associated to some gravity theory. Okay.
Yeah, is this choice of gauge very exotic, or is it one of the choices that we typically?
So for example, for young girls, if you take a stupid choice like Lorentz gauge, it doesn't work. So what these people are doing is there is a huge amplitude thing. They use I don't know what's called Lorentz and various other. They use combinatorial methods to extract things. They even don't know exactly to which gauge these choices corresponds. So they can claim that there exists this choice and it agrees with all things imposed by physics, but they don't know which choice, maybe even non-local or whatever. Okay. So this is basically what I'm going to discuss. So about examples. So let's start to do examples. And of course, the most trivial example, which I'm going to do and try to explain to you what's going on. And, hopefully I will have time to go to less trivial example. So let's do Chen-Simons in R3. And all the Chen-Simons is topological theory, and it's not good to calculate scattering amplitudes, but let's assume for the moment that we can do it formally. So it means that you can at least look at offshore amplitudes. We forget about some issues related to gauge invariance, etc. So we pretend that it's a decent theory. It would be just much easier to formalize it. Also, maybe I will clarify answer to your question, what exactly those objects are not. So we have our Chen-Simons theory, R3, trace of E plus over 3A cube. And then I have to construct the perturbation theory. So see. So let's do a lower again. So in principle, you have to put everything, but if you want to consider only trees, we can just stick to the physical field, so we don't have to add costs. And of course, what I will do, let me do a Lorentz gauge. Yeah, so for Chen-Simons, Lorentz gauge works. So then what you can do is the following exercise, which I will just outline, but sort of it's so you take your guy, okay, and then you basically substitute. So how do you solve on R3 this Lorentz gauge, right? You can just write as A mu. So you can write this as a d mu, some lambda mu A, right? Some another form, or I can just simply. This is equivalent to the flat space, of course, on compact space, this is two different things. So for A of X. And let me, so this is typically what people do. You take your gauge field, you impose gauge conditions, and then I just tried for your Fourier transform. Is 3p x dot p epsilon mu mu rho p mu psi rho a over p. So I solved this condition. The only problem is that this is not uniquely defined, and then what people put this type of conditions additionally on this guy. Okay. So and then you evaluate. So then you just take the things and plug it in there, and then of course you can do a calculation. And
Sorry.
Yeah.
Is this like the equation you just wrote, is that, I don't, why is the A just suddenly a derivative of A versus the?
so this conditional 3. I think you guys talk too much about high structures and forgot vector analysis on 3.
Well, it says AA equals del A.
I mean, it's a vector analysis.
Well, A is co-closed, hence it's co-exact.
Exactly.
On actually, yes, there's no
Yeah.
homology.
Right. So I'm just saying this, I'm solving these conditions. I'm looking at, so I want to evaluate these sections of this condition. Only on the form satisfying this condition. I have to parameterize this choice somehow, right? So I'm saying it's okay, let me write my A mu. I'm using Fourier transform as epsilon p and this guy. So this is the way to parameterize to me the space of these guys, because I don't want to, I want to evaluate on the image of the diagram. Okay, so you do this calculation, which is again just vector analysis, but it's very instructive to do. And then you have this term A, the term AB. It goes to the following thing. So I will let me just write for you the answer and then explain what we are talking. D3P psi mu A P psi B mu minus P mu P square eta AB. So this is eta mu P. This is just epsilon mu for contracted this. Okay. And then another term I will evaluate will be correspondingly eta A B C. A B C. So you actually get here 3 integrals of P1, P3, P2, P3, P3. Then you will get this size sigma A P1 psi B gamma P2 psi phi C P3. Then you will get some guy. So let me write symbolically sigma gamma rho P1 P2 minus P3. So it's a result of concrete calculation. But I will tell you what's this object size at the moment. Okay. And again, I will come to fancy definitions what we are doing at the moment. But if you do too fancy, you can overlook some fact, and that's what happened in the literature. So you just get this. So this would be your propagator. So then what is your Feynman rules now? Sorry? Sure.
The other side, it raises slightly better.
Well,
Yeah, turn it around, turn the thing around, yeah.
round. Oh, complicated system. Okay, so what do you get? So you will get on your propagator, you will get this guy. So you will have A mu, B nu, And then you will have correspondingly A mu P over P squared eta AB. So this object, as always, I assume, I'm just in Euclidean space, I allow race using metric. And again, actually, this guy is inverse of this guy sub to P squared on the space of these things. And then I will have another object, which, so now I will have my, so here I have P, here I have P1, P2, P3, and then I will have indices A mu, B mu, 0. Okay.
Sorry, could you remind me where the nu or the mu or the nu is living? Like the
So
second.
it's this is just one forms on R3. So this is the
Okay.
indices. A, B, C. This is for the just Lie group. So then, if I write this object, so basically, if I write the things, would be the following. So it's mu nu gamma rho P, and then there will be F, A, B, C. So I'm not writing momentum P. What's important thing that you do one explicit calculation and you do this explicit calculation. And what's important that what are these objects are. So in principle, what you can do a totally different calculation here. So let me introduce for you a basis of vector preserving vector fields on R3. So if I introduce those guys, so it's a basis. IP of X will be epsilon mu rho P mu dx. So any vector field which is volume preserving will have this representation, and I'm just expanding as the plane waves. If you want to take some non-trivial, you just write this with integral with some. That's it. So this is first order operators that you can ask, can I calculate the Lie bracket of those guys? So if you calculate the Lie bracket of those guys, and what you get, so if you do this calculation or you do that calculation, so you get exactly this guy. So you will get exactly F mu nu rho P1, P2, P3, and rho P3. So what I can do, I can organize to you a perturbation theory, which on Simons again for trees in the following way.
What is P3?
It's a moment, right? So
Which one?
well, they will be delta function always, right? But I have to write any commutator of elements in terms of these guys. So they will be delta functions, these two guys. So P3 will be equal minus whatever. P1, right. So it's just form of writing. Okay. So then what one can say is the following, that you can look at your perturbation theory is organized in the following way. You have your structure constants for volume preserving diffeomorphisms. You have your structure constant for Lie algebra. Then this is basically analog of invariant metric, because if you, again, this is a question of calculation. If you look at this guy, if you use the delta and your race index, this will be antisymmetric in all data. So it's invariant metric. And here you have a metric for Lie algebra, and you have this invariant metric here, and then you have this P square, knowing this P square. So this is exactly, so what you will have to construct now. So C guy is constructed from this data. Then N guy is constructed from this and this data. And then of course you will have a lot of P squares redistributed. And this is exactly this DIs. But what's important thing is that in this choice of gauge, you can see explicitly that if I will look at these diagrams and will write to you these things in this gauge for ns plus nu plus nt equal to 0, then this will be automatically satisfied. Again, there are two components for the things. It's not only this structure constant, but then I also have this analog invariant metric. Okay. So let's discuss this a bit more abstractly. Any questions?
What is the context? The kinematic algebra is which the algebra, like does it ever mean?
Volume preserving diffeomorphisms. I mean, well, it's for this particular example. I mean, life is much more simple. There are no simple names. You basically have to see theory by theory. So,
The color dependent on the choice of particular Leo.
but kinematics, it depends on the theory. For different theories, you will get different, different rules of doing kinematics.
So in term assignments, I can choose different colors, like different Lie algebras.
Absolutely.
But you're saying each time the kinematic algebra is volume
No,
preserving.
no, no. I'm saying is I give you one theory. There are millions of theories, right? I give you a very, very toy model. I mean, Chern-Simons, and I give you Feynman rules. And here I'm very lucky. I know how to identify rules, etc. I told you that kinematics algebra will be controlled by this operator. If I go to Young Mills, four-dimensional Young Mills, the same will be true. But identifying this kinematic algebra is very hard. That's what I'm saying.
But even within term assignments, when you say volume preserving diffeomorphisms, you mean of R3.
Fast read, right?
And how does that depend on the choice of gauge group for this term assignments?
It does not depend.
Okay, so the kinematic algebra is somehow independent of the color choice for term assignments.
Right. But of course, what's important in this story, it's not that you can construct some gauge theory for, I mean, which would give these guys without these guys. So, Anyhow, so let's talk maybe, a bit more formal, what is going on. And what's the algebra we are doing. So first we'll concentrate on one forms and then, so we have a one forms, right? And we also look at the setup when we have a metric. So we of course have through the metric identification with, vector fields, now manifolds. So my vector fields here, right? So I have my vector fields and then I have one forms. And of course, there is a fact which most of you know very well, it's the following fact that if I take here the algebra, vector fields, then I can rewrite my Lie brackets, for example. Again, it does not depend on the metric, but if I take this algebra and map things here to one forms, then basically I can have here the following. I don't remember the signs, but something like this. I would have minus V W minus V T. I don't know. It's a obvious fact. People, do you know this fact or not? I don't know as much. That bother you, or you know this thing? You don't know.
No, it doesn't bother.
Okay, it doesn't bother, right? So the algebra vector fields, you write it down. You write slightly, you write covariant derivatives, then you raise lower indices, you move to forms, and this would be a Lie bracket. So of course, most of you know that the Dagger operator induces a Lie bracket on differential forms. Okay, so this is a short fact. Right, so now when we talk about volume preserving diffeomorphisms, right? So when we look at volume preserving diffs, So we typically look at this condition. Again, I'm on R3. Otherwise, you know, there are different subroutines. And of course, this is exactly both, you know, if I use symmetric, it will go to this condition, to dagger of A equals 0. So what I'm doing in this weird calculation here. So of course, on this subalgebra, so I have Lie algebra on one differential forms, right? I have a Lie algebra. So this bracket is generated by the dagger. Then this is a subalgebra. So I have moreover on image of the dagger. Right, so this is image of the dagger. Well, it's a kernel, but it's the same as image in the R3. So I will have another subalgebra. So this is a subalgebra. So this is the subalgebra of this algebra, right? Simply because, as you can see, if I look at any objects A, B, which would satisfy, you know, will be the dagger of something, then I will get here, this will be the dagger of anything, right? So this is condition is closed.
Sorry, Maxim, I
Yeah.
don't want to look at what, but is this it's an average generator.
Yeah. But typically, when you look at these guys, you don't look at, for example, algebras of forms with some conditions. But you can start to look at them. There are something interesting. So I'm now restricting on the forms, which is an image of the dagger, which is the same as the kernel of the dagger on R3. Now, what's very important thing, so far it's very, very trivial things, but what is this guy is staying here? So actually I can introduce for you, so I can introduce a pairing on one forms in image of the dagger in the following way. So let me say that my form is a dagger of some psi A. And I will tell you that my pairing is defined as A, B, AC as an integral of form A, which so this is a definition, my pairing. So I take two forms, which is the image of the dagger, and I compare them if I write the integral of A with actually a two form. So then it will, it's exercise that it's a pairing. It does not depend on the choice of psi. You can prove, for example, in this degree, it's actually symmetric pairing, and so everything sort of works out here. Okay. So now, what are we talking about? So now we go back to this form. So what we were doing, we wanted with you take a Chern-Simons and evaluate this Chern-Simons on the image 6 FAB on the image of the dagger. So what you can do is the following thing. So this is a very simple exercise. So every form can be written as the dagger of psi. So eventually I can write this as follows. So let me write for you the answer and then explain to you. So number 6 FABC. Okay. A3. C. So what's important thing is that so this pairing, this is invariant pairing for that bracket. So basically what I'm doing here, right? So when I'm looking at this term, I'm looking at this term, A, B, C. So what I can do is, I know that I'm evaluating on the image of the dagger. So I will have something like this, A, B, D dagger of size C. Then I can write the things as, there is D dagger satisfy, although it's not derivation, satisfy the property of the integral stock theorem. And then this would be a bracket, and these guys with these guys will give me a pair. So I have a pair. So now you see everything looks sort of perfect. If they wouldn't be any Laplacian, you have exactly, usually a bracket, and then you have pairing and a bracket for this algebra. Okay. So this is basically the explanation of trivial things, but here what's important that, this structure of bracket that it's around, it's easy to predict, but you need a pairing. Okay. So now I will speed up a bit. Any questions about this stuff?
This is similar to this last gravity. This formula, like this formula,
Is it similar to what?
gravity. Field theory. Gravity.
Cadaris, no. Look, it's a totally different story. The thing is that, okay, let me put this way: the sum of the formalism which Cadaris spends, these guys were using, etc. Of course, it's very, very similar in the spirit, but they're solving different theory. It's a 6-dimensional theory. I'm doing 3-dimensional theory. But you're absolutely correct to say that certain formal things looks very similar. Absolutely.
Maybe more on the formal side. Right now you have, instead of Lie bracket, that Poisson bracket, right? And delta, would it interact with that bracket similar to the round differential? Or what are the properties of delta in relation to your Poisson bracket?
And by delta you mean what?
That guy, right? You have AA, delta, AB.
Yeah.
Right? The operator.
Here or?
No, the previous term, right? In the
Right.
quadratic term, you have delta.
Right.
In the cubic term, you have a bracket.
Right.
What's the relation? Do they satisfy some nice relation, delta and the bracket?
No. Sorry, I didn't say it. So sorry. Thanks, Anton. So delta, it's a stupid Laplace.
Good.
Right.
And
So then nothing. Well, nothing you can say about the thing. So if there wouldn't be Laplacian, you would say that you even have volume preserving deformation the symmetry of your theory. But because you have this Laplacian, things becomes pretty ugly. So this is why I have all these factors. So this Laplacian is responsible for these factors. I cannot remove them.
so I don't want to remove it. I'm just asking whether they satisfy some algebraic relation, the Laplacian and the bracket. Right? Before the
Laplacian and the bracket, I don't know any simple.
okay.
So Laplacian, it's a second order operator, and
Okay.
not that I can think of any. Of course, it's commute with D dagger, but that's otherwise I cannot say anything simple. But I can imagine that they can satisfy some relations on, I don't know, on bigger collections of this, but I don't know anything simple.
Mhm.
Okay, good. So then, of course, formally you can start to repeat the story, and you can go to, just let me make some comment to full scale PV, which in Simons, and then actually you will see that, you shouldn't now call that color kinematics will be, color algebra will be exactly volume preserving, guys, because the ghosts, I mean, will sort of work differently. But the idea is exactly the following, that what you will have this AKZ type of construction, sigma 3 to G1. Okay. And then you will have favorite deviation, which you can write is 3 theta. Then you have the superfields A, operator D. Okay. So now D is just a DRAM, right? So D is just a DRAM, but I understand this like this. And then, of course, formally, everything I told you now, you can do for, so one forms are not important. So I can look at these brackets not on one forms, on all forms generated by the dagger. I can look at this period, not restricted to one forms, but on all forms, and whenever it's not zero. And so formally, what I can do, I will get for you exactly. So if I impose my, so I have this D dagger of A superfield now. So if I will get exactly the same formula. So now what we would like to formalize why all this stuff is working. So here we have a D dagger, which is just a DRAM. So if I look at this thing sort of abstractly, then there are the following properties why it works. So first of all, so I have my here some DJ with operator D. And I have to pick up some operator D dagger such a way that it's anti-commutative with D, it gives a Laplacian. So of course, all concrete examples of the theories we are appearing, it's a collection of forms. They're always Laplacians, and you always have these p squares floating around. So these guys can look very exotic, but they both should anti-commute to standard Laplacian. And of course, my algebra should be organized in such a way that, I mean, it's close to the Laplacian. Hopefully, I will have time to give you one less trivial example. Okay, so this is property 1. Then property number 2, it squares to 0. Then next property is a D dagger of A. B is equal to -1 A D dagger of B. So I need for this period. Right, so these two properties, and then the fact that I have a bracket is that D dagger is a second order operator. And the order of operators, if you don't know, you can define formally for the algebra. It's just depending how many nested commutators you have to do before it becomes 0. Okay, so this is sort of peculiarity of the gauge fixing we are doing. So we have these properties, and then on the top, we have a second order which guarantees us, for this to be a Lie bracket. So in more complicated theories, typically, for example, I'm not going to talk about physical Young-Mills, but in physical Young-Mills, you can find operators satisfying this. Then you can find this operator, which is not quite a second order, it's high order, but it becomes a Lie, I mean, it will generate a Lie bracket on cohomology, so it's on the shell states. That's why you need to stick on shell state, etc. So these properties, second order, it's very, very good. It should be modified. So let me give you a less trivial example, unless there are some questions.
When you say in Yang-Mills, it generates a bracket on cohomology. What degree is the bracket?
You ask too much. No, I don't want to talk about Young-Mills. So it's an operator. I think they will be 5th degree, etc. And then,
So, I don't mean degree as an operator, but degree as
there is a degree. Sorry, it's maybe not the word degree. It's order of operator. It will be 5th order operator.
But I'm not asking about the order of the operator, but the degree as an operator shifts in the Lie bracket. If I take a bracket between an A form and a B form, the bracket induced by D plus, what will the result be?
No, Didagger is always degree -1. So that's what I mean. It will be like, I mean, this type of bracket. But again, the problem is that generically you should not expect that this bracket will satisfy Jacobi. But in all examples, if you start to write down, so this is actually, if you look at theories, this is very, very severe conditions. So if you work them out, it just puts you in the theory very particular operator, and then you have to start to study the things. So actually what I don't understand, I think this is of conditions is very, very important, but it's sort of hard to understand because Laplace operator by itself is operator of second order. So I don't know how many D-daggers, so what, in what sense, I mean, D-dagger is differs of usual D-dagger. So let me give you one less trivial example. So I'm not ready to talk about 4D Young-Mills, but we can do a kindergarten version of Young-Mills. Let's do 2D Young-Mills. 2D Young-Mills. So 2D Young-Mills, this is just a theory, which of course you can write as FA, H star, and B, eta AB, right? So you have some algebra, you have field strengths, or typically what people do, most of the people prefer to write the first order formalism, and you write FA, D, E, B, eta AB plus 1/2 phi A star B, eta AB plus 1/2 phi A. So there exists, I don't know if it's standard or not, AKZ construction, which you can write the following. So you replace this DGA by slightly different DGA. So you have the following DGA: 0 form, differential 1 form, differential 2 forms, and then 0 form, 1 form, 2 form, DRAM, multiplication by volume. So this is DGA. Now, if you want to do something, so let me write this superfield here, A of x of theta, and this superfield is a C of x of theta. What I can do, I can combine them to one superfield if I introduce another psi of degree -1. So I introduce Fermi guy, then I can write something the follows. So I will write my superfield now, x theta and theta, as A x theta plus psi phi x. And then in this picture, my operator P is just a DRAM plus volume derivative of x. I don't know how much it's familiar, and Pavel is expert on 2D Young-Mills. But again, I don't think it's anything exotic. It's maybe known to experts. But what's important thing that if you use this formalism, so if you use this field A, then this is just a Chern-Simons section. So if you write your thing, then this is just A, D, AB, AB plus F of A, C, eta A, B. You just take this this differential and plug it in. If you evaluate at physical fields, this is exactly the section, section size. Then you can ask the following question: okay, can I find the operator which satisfies these things? So surprisingly, it's not such a trivial problem to find. But after work, you can find it, and you can actually say there are not so many operators like this. So let me write to you some diagram. So this is the Dagger operator. So actually all these coefficients are fixed, they are not arbitrary. If you want to impose all properties.
Upstairs, is it omega 1 in the middle?
Yeah, thank you. And this is I. So either this or it's complex conjugate. Nothing else you can find. So you can write this guy in superfields, of course. This will be a second order operator. So again, you look at gauge fixing abstractly, you just start to write some ansatz, you run down. Eventually you have to satisfy all these properties. And then you see if you operate second order or not.
So this diagram defines a D-dagger.
Exactly.
D-dagger.
Right, absolutely. So it's a D-dagger, which of course, if I want, I can write in superfields, but it will take time. Then you can check explicitly. But finding and classifying sort of takes some time. Okay, so let me just make up short. So what is this operator and what's algebra we are getting here? So this is, for example, when the algebra is totally different. So here, actually, if I would look at the kernel of this D-dagger operator on the physical field. So let me look at physical fields. Physical fields. So my gauge fixing actually will be this one. Once you complexify, you everything here. So this is gauge fixing. So if I take this gauge fixing and now plug in into this action, I will get the following. So my action for the trees will be the following. So this will be minus D-dagger of A10. Let me skip star color indices. D-dagger of A01 plus 2I D-dagger of 10 and then A10, A01. Okay. So what did we get? What's the pairing and what is going on here? So the pairing between these guys, so if you work up this stuff, so this is what just give you Laplacian. So the pairing here, so the pairing between 1,0 form and 0,1 form, this pairing would be just what you would guess. Okay. Now the bracket on your forms 1,0 form plus 0,1 form, it's generated by D-dagger. And you can check.
I'm a little bit confused. If you apply star to 0,1, don't you get 1,0 again?
Or if you apply star, you just put either I or minus I, right? So this is the way you can forget, you can just put here minus I or something. So, but this is sort of the standard things people use. But now what I want to outline that there exists a bracket which imposed by D-dagger. So now D-daggers treat these two spaces differently, of course, because for example, bracket for these guys is identically 0. Bracket for these guys, it will be sort of the normal holomorphic version of vector guys, and then there will be action of this space on this space. And this is invariant. So actually, you basically can write the same form which I was telling you before, that you write 1,0 Laplacian 0,1, plus you will have this pairing between 1,0, 1,0, B0,1, etc. And then, so your tree diagrams for Young-Mills will be organized, for example, in this type of things. Again, let me stress that if you start to look at the gauge fixing from that end, it looks sort of pretty exotic because it's not what people do. I mean, our hunt is basically to look at Chern-Simons perfect situation and try to formalize all these properties, try to look at ansatz and hopefully try to find as minimal order as possible of operator. And it's sort of possible. There are more examples I can tell you. And of course, once you go to physical theories, the story becomes even more complicated. And gauge fixing, which would be involved, becomes much more complicated. And it's an interesting issue to classify them, to see what's going on, etc., etc. It's not that we have a proof, but anyhow, we are moving in that direction and of understanding of this formal structure. So sorry for overrunning for 5 minutes. Thank you.
Questions?
So it looks like a very beautiful story. So you traded one algebra structure to another one, which looks interesting and in some way exotic. But is there some does it help computing some some new properties of diagrams or of your expansion? That's an interesting symmetry, but does it have some interesting corollaries?
Absolutely. So actually, this is a major method of calculating diagrams in the gravity. So people believe in this experimental fact and so much stuff that they do, for example, for the gauge theory, they have to find this gauge fixing when your kinematic factors satisfy the things. And then they believe, because of many checks, that if you square this result, it gives you some scattering in the gravity. So calculation is so efficient that it's even least used for gravitational wave. But it's not proven. I mean, so people just believe it because so much evidence for 15 years. So it's basically now up to people in math community to understand. There are a lot of attempts, a lot of observations. But of course, it's very, very hard because there are many, many theories, and it's very hard to formalize that. So it's not a simple problem. It's not that you can come and say, oh, everything is L infinity. But for amplitude people, it's very, very important because it's actually a major tool to calculate gravity amplitude.
So in BV, gauge fixing is a choice of other branch. Is there like an interesting geometric interpretation?
Yeah, this is Lagrangian also.
But this particular one that seems to have particular properties.
That's curious question. I mean, typically in BV community, we look at at gauge fixing like second class people. I mean, it's not important, right? You write a KZ action, you do the things, but gauge fixing is not important. Here you start to see that if you pick up very peculiar gauge fixing, you get something is going on, etc. And
I guess also another question is it homotopic to other choices, or is it like a sort of isolated Lagrangian?
I have no clue. I have no clue. I mean, for example, if you start to look from point of view of normal people to this gauge fixing in the young mill, this looks strange, right? And so I don't know, is it equivalent or not? But in a way, if you try formally to find the operator with all these properties, which looks sort of natural, you find this operator, then it tells you that you should have some sort of this complex version of Lorentz gauge involved in scalar field. Of course, it's a valid question to say, oh, maybe it's another theory, maybe this Lagrangian is not homotopic to whatever Lorentz. Maybe, I don't know.
Yes.
Yeah, I don't know. I think it's interesting questions, and I don't know.
Any other questions?
Just a follow-up, Mike. So when you introduced this like kinematic algebra, the motivation was through using just three particular diagrams, three particular graphs. Like just to piggyback on that question, if I were to write out larger and larger graphs, is it just that this particular gauge happens to pick out something that satisfies Jacobi on the nose as opposed to Jacobi up to L infinity?
Now, people won't like, I mean, so typically would like this to satisfy exactly Jacobi. And I mean, up to whatever this on shell conditions, so contact term, but they need actually Jacobi, and that sort of makes life very, very complicated. And all this business of on shell states make life more complicated. I mean, I look at topological theories, I sort of avoided to discuss the things, but on shell states, I actually will be related to cohomology of these operators and stuff like this. So you have to, I mean, you start to get more and more rich structure there. But eventually for calculation, you need the algebra, and that's why it makes life much harder.
Thank you again. And at this point, we'd like to ask you to join us just out on the steps outside for a conference photo. It'll be real quick, and then we can have coffee and we'll meet back here.